Suppose we have an arrow pointing in this direction. Its length tells us how long it is, but a single number can represent both its length and direction. So how can we represent both using numbers? We can represent it with a vector. If this arrow goes 2 units to the right and 3 units up, we write the vector as 2, 3. If we place a vector at the origin, its endpoint will match its components. So a vector 2, 3 starting at the origin ends at the point 2, 3. That's why we often draw vectors starting from the origin. Remember, the vector itself is not that point, and we can move it anywhere without changing the vector. Now we know how to describe the direction components of a vector, but how do we find its magnitude or its length? To make this easier to see, let's look at another vector, 3, 4. We use this special notation, which looks like a double absolute value, to represent its magnitude. To find the length, we can draw a right triangle. Notice that we're only missing the length of one side, so we can use the Pythagorean theorem we learned before to calculate it. Substitute the known lengths, then isolate the magnitude of v, and we get a magnitude of 5. Now we have a vector in 4 dimensions. Yes, vectors can have more than 2 components if they're in a higher dimensional space. How do we find its magnitude? The answer is surprisingly simple. We follow exactly the same pattern. If you didn't recognize it, this pattern of squaring the components, adding them, and taking the square root already appeared in the 2D case when we isolated the hypotenuse in the Pythagorean theorem. We do exactly the same thing here. And this pattern continues no matter how many dimensions we have. I'm going to include a visualization of this in the next video. Vectors have 2 main operations, scalar multiplication and vector addition, and they're actually quite simple. Scalar multiplication means multiplying a vector by a number. We simply multiply every component by that number. For vector addition, we add the corresponding components together. Now, what does it mean? It means that we can only add values in the same direction. For example, a horizontal component can only be added to another horizontal component, which makes sense. Subtraction works in a similar way. We subtract the corresponding components, but we normally don't consider subtraction a separate main operation because subtracting a vector is really just adding the same vector multiplied by -1. Before we move on, I just want you to notice that it's common to use symbols to represent vectors because it makes everything much cleaner. So get used to seeing vectors written this way. Now I'm going to show you how to graph these operations, and yes, we can actually solve vector operation problems graphically. This also gives us a much better idea of what these operations actually mean. For scalar multiplication, multiplying by a number greater than 1 stretches the vector while keeping the same direction. By the way, as you can see, when I double the vector, not only do its components double, but its magnitude also doubles. If the scalar is between 0 and 1, the vector shrinks instead. And if the scalar is negative, the vector also flips to the opposite direction. For vector addition, we move the second vector so that its starting point is at the end of the first vector. The vector from the origin to the new endpoint is their sum. We call this the tip-to-tail method. Why does tip-to-tail work? Let's break both vectors into their components. Since moving a vector doesn't change it, we can rearrange them and combine the components in the same direction. And look, the combined components form exactly the resultant vector. Vector subtraction means adding the opposite of the second vector. So we first reverse its direction, and then use the same tip-to-tail method. Of course, there's much more to vectors than this. I'll talk about them in future videos.